Okay, so where we left off was talking about internet stuff, packet switching, and the TCP/IP binary backoff algorithm, and we finished up with that yesterday. So, next stuff, network functions. So we'll talk a little bit about APIs, and then we'll talk a little bit about the 7-layer OSI model and TCP/IP. That'll be pretty much most of it today. So first thing, networks include a lot of different components and technologies, right? So there's Ethernet for wired connection, there's Wi-Fi for, normal range wireless, there's Bluetooth for very short range wireless, there's fiber optic cable, there are cable modems, there's DSL in some places, it still exists. There's circuit switching, there's packet switching, all kinds of different technologies and all kinds of different applications. So question is, how do you make all this stuff work together? Because it's not as easy as you might think, right? I mean, how do I take an email application and make sure that it runs correctly through some kind of medium, whether it's wireless or wired, and how do I make sure that the application on the other side is prepared to receive it in the proper format? Okay, so that's the issue. Well, the nightmare scenario would be this. For example, if you're doing web browsing, it has a different way that it conforms to each one of these technologies. Likewise for email, different way that I have the camera on.
I understand.
Okay. Yep. All right. Anyway, just let you know in case you're just going to walk around in your underwear or anything.
I'm not.
All right. So you say. Anyway, email could have all these different ones. BitTorrent, if any of you use that, could all have different interfaces for all these technologies. Now the problem happens, right? So that's bad enough, is that for any new application you come up with, you have to develop new interfaces for all of the existing technologies. But on top of that, if a new technology comes along, right, like a new generation of cellular or Wi-Fi or Bluetooth, well, guess what? Every application out there has to develop a new interface to deal with that kind of technology. That's a huge headache and is going to be a major drag on designing anything new. Because anything new that you bring out, if people are going to use it, it has to have all those interfaces in place. So, all right, same for VoIP. All right, so a lot of work to add new apps or new media technologies, and it's going to limit growth because it's going to be more work to develop them. It's going to limit adoption because it may very well be that the new technology is not compatible with a bunch of applications or vice versa. So, same thing with others, even if you just have two end users that are using the same application but on different technology, how are they going to interface? Okay, so the basic method of dealing with this is something called indirection. You have a magical abstraction layer in between the things. And the essential idea is this. We talked about packets earlier. The idea is any one of these technologies is going to use the same kind of packet structure. And based on that, that means whatever the underlying technology, right, whatever the application is, it's going to format its data the same way. And it's going to be transmitted in the same way, just over a different, through a different technology. For example, if it's wireless, it'll be through a wireless card. If it's over wired, it'll be through an Ethernet cable. But the packets will be structured the same way. And that means as far as the application is concerned, it doesn't have to worry about any sort of special interfaces. That's going to be handled somewhere else. And this means anytime you bring in a new technology, you just have to make sure that it's conformant with the regular packet structure. Likewise, anytime you bring in a new communication medium, you just have to make sure that it accepts and sends out the proper format of packets. So that's great. And that's one example of an API, which is Application Program Interface. It's a way of letting your two applications communicate by converting the data into a standard format. Okay, so that is a pretty key concept. Anyway, this order one work to add new apps and new media. That simply means you just have to add on one connection to the interface, right? You have to add in, it has to be formatted for the interface, and that's all you have to worry about. This order thing is a way of describing how much complexity there is in developing a task. For example, if you had to develop a separate one for every one of N technologies, a separate interface for every one of N technologies, it would be order N. If you had to consider the entire pool of interfaces, if they all had to do that, then it would be order N squared. But order one, that's as easy as it gets. You build the one interface, it conforms to that, and then you're good to go. Okay, now this is part of what's called layered technologies. So the core idea, remember I said a minute ago that if we had these, the magical network abstraction layer, if I design a new application, I just have to make sure that it conforms to this packet model. Well, the way that works is through this sort of layered technology. So at one end, we have the application. You have an application that's running on your machine. It wants to send data to another machine. Okay, so that data gets processed through a whole bunch of different tasks until finally it gets sent out, right, through physical media. It gets sent out as transmissions, whether wireless or wired. Now, there are different ways to do this, but the key idea is that each layer performs a specific set of tasks and receives a standard input and produces a standard output that's readable by the next layer. So the nice thing about this, for any of these layers, as long as it properly accepts the input format and properly produces the correct output format, we don't need to know anything about what goes on inside it. So the application, if it wants to send a communication out, it says, well, all the application has to do is worry that its output format is what layer N here expects. And layer, you know, all the way down to layer 2, all layer 2 has to do is say, if my output conforms to layer 1's requirements, then I'm good to go. No individual layer needs to know everything that's going on in that entire stack. It's a wonderful thing. So the interfaces define these cross-layer interactions, and they only rely on those below them. That means as long as layer N here accepts the proper input and produces the proper output, that's all it has to worry about. This makes your system incredibly flexible because you can, number one, reuse your code across the network. So you can pull out a layer, for example, and implement it somewhere else, and it's going to work the same way. It's going to accept the same input, produce the same output. So it doesn't matter what hardware it's running on. The other, module implementations may change. I can change something within this layer. For example, if down here in layer 1, which is typically something like transmission scheduling, I can come up with a different transmission scheduling scheme, and that's not going to affect anything that any of these other layers do. As long as layer 1 here still accepts the packets in the proper format and produces the proper set of signals to go to the physical media, it's all good. I can change that in there without affecting the rest of the system. One thing that's a bit of a trade-off is that your system will not perform quite as well as it could, because every one of these is a little bit of a translation involved, so that's part of it. But the bigger thing is simply sometimes there's data that could be shared across layers that could make the system run better. For example, one of the things we talked about was this binary exponential backoff. And the way we talked about it is every time a transmission fails, the device is going to wait twice as long for its next transmission. And that way, over time, it'll generally conform to the population of devices that are trying to communicate, and there won't be too many transmission collisions. But it would be possible to do a whole bunch of things across layers if you made that data available to everyone. For example, if you had, as one layer, learned how many devices there were in the vicinity and shared that across layers. And then in various ways, you could more closely optimize what's going on. For example, anything in terms of sending packets out into the network, you could recognize, oh, the network's not very busy now. I'm going to send out a whole bunch of packets while it's quiet. And I'm going to skip some of these tasks as far as, you know, figuring out when I can transmit and when I can't. I just recognize, oh, right now it's quiet, so boom, I'm going to use it. But that involves sharing data across layers. And the problem becomes, if any of your assumptions change about how that population is measured, that could have other effects on all these layers. So you have to be really careful to say, if I'm going to change something in one layer, is that going to have consequences for the other layers? If you do a true layered application, it doesn't. All the layers are self-contained modules, and all they have to worry about is whether they accept and produce the proper inputs and outputs, respectively. Okay, so key takeaways: layered network stack. It's modular. Each layer fulfills a limited set of roles. Inputs and outputs are highly standardized, which means that each layer only has to worry about what it's doing. It only has to worry about accepting a proper input, if it produces a proper output, it doesn't need to know anything else about what's going on in the system. And that makes it very easy to change layers and very easy to, transfer that system to other hardware. Okay, and the trade-off, of course, is your system's not going to be super optimized, but generally speaking, systems are fast enough, powerful enough that that's a pretty good trade-off to make. Okay, now, key questions. Like I said, there are many different ways you could set up this kind of layered system. So how do we divide it? Well, there's a few key things, right? Number one, things like routing. How do we actually address the packets to make sure they're going to get to where they need to get to? Number two, congestion control. How do we prevent all the devices from transmitting at the same time and causing massive collisions? And last, error checking. So if something goes wrong, can we detect it? Do we recover from it? How do we recover from it? All right. Don't have all the answers for these, but rest assured, if you take some 500 level courses, they'll talk about these issues. I used to teach up until this semester. I taught the first half of IDS 520 network infrastructure, and yeah, we spend a fair amount of time there talking about things like routing protocols and associated issues. Anyway. So if any of you come back to do a master's in MIS, you'll probably take that. And the guy I handed it off to, for now, he's doing mostly what I had. So who knows, maybe he'll still be the same way. But routing is pretty fundamental to networking, so you're not really going to get around that. Anyway, other thing, how do we distribute functionality across devices? So for example, something simple like security. I say simple. So here's a question. Who is responsible for it, right? So if I have a device here on the left and he's sending data to this device here on the right, it's going through a switch, which is a direct connection, and then through a router to get to another network, and then to another switch, and then to the machine. Where are you going to check to see if there's something wrong with the system? For example, if I send a corrupted email, right, some dangerous bit of malware as an email attachment, you can't rely on the other guy, right? You can't rely on the other guy to be checking that, because if I'm sending it, I might be a bad guy. I might be deliberately sending it. So if you rely on me to be good, then guess what? That system is very easy to exploit. On the other hand, right, if it's all on here, well, yeah, you could test it there, but wouldn't it be nice if the router could provide some sort of testing and prevent that malware from even getting to the device in the first place? So yeah, some of that happens. Depending on what system you're in, what technologies, there are various ways where routers do attempt to detect malware. But the point is, it's not something that you're going to typically implement just in one place in your network system. The other thing, fairness. For example, if I have a bunch of devices, one of the basic things with your standard TCPIP connection is that once a device grabs hold of the channel, it tends to use it more or less exclusively for a long time, right? So once I start sending out packets, if I have a long sequence of packets to send, I'm going to keep on sending them. And if there are a lot of devices out there, then they could get choked off, basically. They might not have a chance to transmit their data when they need to transmit it. So this is the sort of thing you have to be aware of. Now, depending what application you're using, there might be some sort of group application where you can automatically schedule participation by individuals. There are other mechanisms just to prevent individual devices from hogging the channel a long time. But again, in many applications, you need to make sure that everybody has a chance to use the channel. Otherwise, the network is not going to be really fair. And people will ask, well, what am I paying for if I can't use it? Okay. So again, don't have the answers for all these, but these are, just big picture questions to give you an idea that, hey, this layered thing, it sounds good, but it's not going to solve everything. There's still a lot of policy implementation issues on top of that. Okay. Now, when we talk about networking, we, of course, typically mean communication between machines and typically over the internet. Now, in networking these days, standardization is the rule because nobody wants to reinvent the wheel, right? This isn't like 1960 where everybody's still learning how to do it. There's a lot of experimentation going on. Nowadays, networks are well established, and sure, there's people still working on new technologies, new setups and stuff, but networks are widely implemented. So everybody just wants to get it in, get it working, and they don't want to spend too much time designing stuff. Anyway, one of the key models is what's called the 7-layer OSI model. Now, back in the day, and when I say in the day, I mean circa 1970, there were two main models for how the internet might be set up. One of those was this 7-layer OSI. And if you've never heard of it until now, well, the reason is it never caught on. The other one is TCPIP, which we'll talk about in a moment. Now, the nice thing about 7-layer OSI is that it specifies everything that was supposed to happen. So in a sense, it was more of a philosophy of how to set up the network, right? The exact tasks, sure, they had a setup of the exact tasks required, but the point of 7-layer OSI was it was going to specify exactly how the network should work. And basically the problem with that is all the top people involved in it got so caught up in meetings and arguments about how it was going to be set up and how it was going to work, they couldn't agree on a common solution. And so it just dragged and dragged and dragged. Meanwhile, TCP/IP, much more flexible approach, you know, while the OSI guys were off in a room trying to figure out how they were going to do it, the TCP/IP guys said, bye, see ya, we're going to go build the internet. And that's basically what happened. Because they didn't have to answer all the questions, they could, in a sense, agree to disagree and still go about building the networks. Yeah, TCP/IP got moving before OSI got off the ground. Anyway, but OSI is very good for teaching purposes because it takes all these basic layers and explains exactly how they work. So it's nice for teaching purposes. This bit here, again, talks a little bit about cross-layer information sharing. Now, again, 7-layer OSI, it is a strictly layered system. Every layer in the model, right, these N layers that we had a minute ago, it has 7 layers, and they're all strictly separated. Every one of them accepts input, produces output, doesn't know anything about what's going on. Now, of course, as I said, if you were going to share information across layers, you could in various ways optimize your system to run faster. And if you want to do like a search on Google Scholar, you can say cross-layer network optimizations and find a bunch of research with people doing on that. But the basic trade-off is that yes, you can make your system perform a little better in terms of how much data it can push through per unit time, but the trade-off is your system's going to be less flexible. It's going to be harder to expand or otherwise modify, because anytime you change something, you're going to have to be aware of how that's going to affect the rest of the network. Okay. Now, 7-layer OSI model, the layers, physical data link network transport session presentation application. Or you can look at it the other way, going backwards. So this one, physical to application, this is for receiving data, right? I receive data at the physical layer, that's your network communication medium, and it goes through a bunch of processes all the way to your actual application that's running on your machine. So let's talk about these. We'll put it in Paint. Okay, you can come up with a snappy mnemonic for that. 1, 2, 3. Okay. And if you wanted to, you know, again, the mnemonic, all people seem to need delicious pizza. Okay, you can probably come up with a mnemonic that's funnier than that, but there it is. All people seem to need delicious pizza. It's a fact. Anyway, so what do these things do? Well, you have here, I'm going to copy over on one side and copy it over to the other. Now, anytime you're sending a message around, it's going to go over to one machine and back up to the application layer. So put up here, message start and message received. Okay, so you have two applications on different machines that are trying to communicate with each other. Basically, that means you're gonna say you send some email. Okay, that email is eventually going to get chopped into packets and sent over the network and received by the other device. So Let's put in those steps. So application sends the email. Okay, easy. You press send, boom, it sends a slug of data to the presentation layer. Well, what does the presentation layer do? Well, it's responsible for things like encryption, okay, before it gets sent out into the network, and other formatting, right? So for example, you might do compression at that point. The session layer, one of the things the session layer does is maintain sessions, of course, right, as necessary. So if you're logged into email, it's going to keep that. And, excuse me, and coordinates applications. Okay, so with the session layer, you might have multiple applications that need to run with some sort of coordination. For example, if you are running a streaming video application, you're going to have one flow of packets that's for audio and another flow of packets that's for the video. And you want to coordinate them so they arrive somewhat synchronized, so you don't have the audio segments arriving long after or long before the video segments, right? You want them to schedule them so they go together. You don't want the video to play without the audio being present. Transport layer chops data into packets, right? So what the application layer sends out is a big slug of data, right? If I press email and I've got some big attachment on it, well, at some point that's going to have to happen into, it's going to have to get chopped into packets. That happens with the transport layer. The network layer, responsible for addressing packets, right? To make sure they're going to get where they're going. That's the big thing that the network layer does going out. The data link layer schedules transmissions and sends bit stream to the physical layer, right? PHY, the physical layer. So if I'm going to send out a bunch of data, at some point that's going to have to be converted into a sequence of ones and zeros. Well, the data link layer is where that happens. Okay, so with all of these tasks, we've gone from having this application producing an email with an attachment on it to having a bit stream that's ready to be sent out, and each packet is going to be properly addressed and ready to go. So the physical layer, what it's going to do, actually transmits each packet appropriately. Okay, so the physical layer, when the data link layer says, yeah, now it's time to go, the physical layer is going to say, okay, boom, I'm going to send it. And that's what it does. So again, each of these layers is a separate task. What it receives, the application layer sends an email to the presentation layer. The presentation layer is going to format it and somehow label what each application, what each application the stream belongs to. The session layer is going to group any applications together. The transport layer is going to take all that data, chop it up into packets. The network layer is going to slap an address label on each packet. The data link layer is going to tell the hardware when it's time to schedule, when it's time to transmit each packet, and then the physical layer is going to transmit them. So over on the other side, right, we have these same issues going back the other way. So again, physical layer ready to receive the bit stream. Okay, the data link layer basically checks if this device is the next recipient, right? Basically, there could be a whole sequence of devices that this message is going through. Okay, the network layer checks if this device is the final recipient. Okay, so I'm going to say if it's not, right, if the data link layer looks and says, oh, I'm not the next recipient, I say, otherwise ignores the packet. It's going to say, yeah, I heard this thing, but it's not for me, so I'm not going to process it. The network layer, on the other hand, if this device is the final recipient, it's going to process it, send it upward through the stack. But if it's not, otherwise send it onward, right? which is called forwarding. It's going to forward the packet onward to the next device in the routing path. The transport layer will accumulate packets, okay, to combine into a data stream. All right, so remember, in the other sending out stuff, the transport layer chopped the data into packets. When it receives it, on the other hand, it's going to say, oh, here's some packets going in. I'm going to accumulate those into a data stream for, you know, one or more applications. Session layer is basically going to, once again, coordinate related applications. It's going to make things get processed at the same time together. Presentation layer, of course, if it encrypted stuff on the other side, it's going to decrypt and other unformatting, right? Basically to take this data and make it into some format that the application can read, to application readable format. And the application layer, you know, if this is email, just receives the email and the attachment. Okay, so this is how the OSI 7-layer model works. And all of these tasks, in some sense, they're present in all of these models because they all need to happen, right? There's an application, there's a chance that it might need to be encrypted somewhere. It'll have to get ready to get shipped out into the network. Each packet will have to have a label put on it, and so on, right? So all of these things have to happen in networks as we have them today. So the OSI model is just, you know, one way and a fairly standard way of grouping these. We'll talk more about TCPIP in a minute and see how that changes. Okay, questions on any of this? Are we at a good point? How's everybody? What's happening? Any questions? Anybody gonna drop a chat on me? All right, worth asking, I suppose. All right, so the next thing, switching versus routing. So switching and routing are two different techniques for processing packets. So switching is direct connections between devices within local area networks. For example, if you have a bunch of devices in your house or in a computer lab, that's almost certainly a single local area network. And all of that gets processed at the data link layer. It's all in the same network, so there's no need to do routing across networks, and there's no need to go to the network layer to have things say, is this for me? Because all the devices tend to be directly connected. So that's what happens. So network traffic is generally going to get processed through the data link layer. If you have a switch connection between devices, then every device is going to look, oh, is this for me? And then it'll get passed onward. So the core problem, this is in switching, when I receive a packet, the sender might be connected to multiple devices. So the question is, should I ignore this packet, right? We have a simple, let me get into Paint here. I'm gonna have to reshare in a moment though. Okay, we're back. So imagine we have something simple like this. We have a whole bunch of devices connected to one router that's plugged into your wall. Okay. Okay. And they're all, you know, a bunch of different devices. The router is going to know what all these devices are and where they're connected. So if I, for example, want to send a message to this other machine, I send it to the router and the router says, oh, that device is on my network. Boom, I'm going to send it that way, right? Or if I just had two devices, even if I don't have a router, right? If I just have some hub type device in the middle, and people don't really use hubs anymore, but if I did, right, I could have all of these devices connected to one star in the middle. And again, the hub is a simple device that just echoes a signal out onto all other devices. So if, for example, this red one sends a communication out, the hub is just going to echo it forward to all of these, and each of these devices will look at the incoming packet and say, is this for me? If it isn't, they discard it. And if it is, then they know it's for them because that's the typical hub setup. All right. On the other hand, routing. Routing is for connecting devices in different networks, and that network gets processed at the network layer. Now, the key problem for routing is if there's an incoming packet, is its destination in my network? And then if the data link layer finds the packet is for me, am I its final destination? So what you typically have with routing is something more like this. You have a device at one end and a device at the other end, and it goes through a bunch of intermediate devices to get to that destination, and each one of them might perhaps govern its own little network of things. All right, so I'm just going to draw some of the, the crow's feet for that. You get the idea. So each one of these routers might have its own set of devices that it's governing. And when each of these routers receives a packet, so red device down here is sending a packet to blue device up here. There we go. First of all, this router is going to receive it, and it's going to say, oh, I am the next person for this device, but it's the device that it's for is not in my network, so I'm going to pass it on to this next router. I'm going to know that that's how I get to this other device. Same thing, this device gets it's going to say, well, the device this is for, it's not in my network. I know that I pass it onward, and so on. Eventually it gets there. So these devices, yeah, they receive a packet at the link layer, data link layer. They look at it and say, yeah, I'm the next recipient for this packet. Then they bump it up. They say, is it for me? No, it's not for me. It's for blue guy. But then they look, well, how do I get it to blue guy? Well, it's not in my network, so I pass it on along the chain. Basically how that happens. Okay. So those are the core problems, switching and routing. Now we have a simple package shipping example here. So imagine if I want to send something to my buddy in Australia. If I'm sending a physical package through the mail, it's basically going to work the same way it does to send it to a network. So first of all, I prepare the package for shipping. What does that mean? Well, suppose I'm sending, I don't know, rainbow narwhal. All right, I'm sending this guy. Oh no, better yet, a kiwi. All right. See, when you have kids, you always have stuffies lying around. So imagine I want to send this rainbow kiwi to my friend in Australia. So first thing I got to do, I got to prepare it for shipping. So I put it in a box, right? What else? I make sure the box is secure. I mean, you can think of that as chopping it into packets, right? So I package it, I get it ready to transport. Then what do? I put an address label on it so it can get to where it needs to get to. And I put postage on it so it's properly formatted to go through the postal service. Then what do? I take it to the post office. Post office handles the rest, right? So my interface is just with the post office. I don't need to know how the post office is going to ship it there, right? In terms of I don't need to know what kind of plane it's going to use or who's driving the plane or, you know, when precisely during the day that plane is going to take off. I don't need to know any of those things. I give it to the post office. They handle the rest. Same idea with these layered networks. Now, in Australia, it's probably not going to go through a straight flight. For example, from Chicago, maybe it goes west, it goes to Los Angeles, and then out to Hawaii, and then maybe to Sydney, Australia, and then at some point it gets to, maybe it's on the other side, maybe it's in Perth or something, is the final destination. Eventually it gets there, gets to the post office in Perth, and then they say, this package belongs here. It's in the right place. And so at that point, it gets loaded onto a truck, driven around town, eventually dropped off at my friend's address. He opens it and says, wow, rainbow kiwi, just what I always wanted. Okay. Or maybe he preferred the rainbow narwhal, but you get what you get. All right. So same idea with networks. Yeah. You send stuff, you get it ready to go out the door, and the network handles the rest. And again, this is the magic of these layered systems. The only thing you need to worry about is getting it ready to hand off to the next layer. Okay, the other one, TCPIP, right? So I mentioned 7-layer OSI, that's the one we covered. TCP/IP is the one that's actually used. So every computer and network on the internet use the same protocols to control when transmissions are sent, how packets are formatted, all that. It just makes sense that they'd all use the same way so they don't have to reformat data across networks. Standard protocol is TCP/IP, which stands for Transmission Control Protocol and Internet Protocol. And it covers most of the same functions and sequences as OSI. There is more flexibility built in. The model is you don't have to follow it quite as strictly. And a big one is it doesn't specify a physical layer. Okay, so let's talk a little bit about that. So the 4 layers in TCP/IP: application, transport, internet, and link. I'm going to show you how they bundle in, right? So what we have here is, again, OSI 7 layer, but if we're doing TCP/IP, these are bundled into groups. Okay, so the first one, this goes as TCP/IP application layer. Now, the importance of having all these as a single layer means you can do cross-layer data sharing and also skip layers, right? So for example, if you have an application that doesn't require any encryption or other formatting, boom, you can go right ahead to the transport layer, right? You don't have to go through those other tasks, so that can help a little bit. Right, OSI, you would still have to go through those steps and check some things. What else? I can share data across these layers. For example, I can have an application that needs to know what the state of the current session is. I can do that. So for example, I can go from page to page and make sure that I'm still me, and I can use that session information without having to go back and forth between that layer. The application itself can use that data, which makes a lot of things happen potentially much faster. Okay, the other ones, transport, right? That is, of course, simply transport layer, and it basically does the same thing, right? It chops the data up into packets. The network layer for TCP/IP is called the internet layer, and uses IP addresses. So the addressing scheme for TCP/IP is specified as IP addresses, so internet protocol makes sense. Then the data link layer in TCP/IP is simply the link layer. Once again, basically does the same stuff, schedules transmissions, converts the data to a bit stream, all that. Physical layer there's no physical layer specification in TCP/IP. And the reason for that is really simple if you think about it. You don't need one. If the data link layer is going to send out data in the proper format, then any hardware device that can accept that proper format, accept and receive that proper, accept and retransmit that proper format on the other side, is going to be just fine. Okay, so one of the key things back in even in the 70s, the guys that were computer guys knew that stuff was going to be moving fast, new technologies were going to be exploding. They didn't know exactly what was going to happen, but they knew there was going to be a bunch of it. And they said, this is crazy. How can you even think that you're going to specify exactly how a physical layer is going to work? We have no idea what's going to be happening 40 years down the road. Even if we think we do, we're probably just wrong. So the idea that we're going to specify what the physical layer is going to be, that's just crazy. It's crazy. It's a bad idea. We shouldn't do it. Let's not do it. Let's come up with a system where we don't have to. And the way that they don't have to, again, they specify the output that the data link produces. As long as a physical layer device can handle it, it's good to go. So there's no physical layer in TCP/IP, and that's why. Okay. Excuse me. So again, the message path is basically the same, right? It goes through these steps: application, transport. Here they say network instead of internet, but same thing. Goes through the link layer. At the intermediate stops, each device, excuse me, each device that receives a packet looks at the packet, says, Am I the intended recipient for this packet? If so, I pass it up to the network layer. The network layer, I look and say, am I the final destination of this packet? If no, and we know that they're not because they're intermediate devices, it kicks it back down to the link layer to get retransmitted. So it's going to go zzz and then up and then back down and then back up and then back up until it finally gets to its last spot. It says, here's a packet I received. Is it for me? Yes. Push it up to the network layer. Network layer looks at it and says, am I the final destination for this packet? Hooray, I am. So at that point, you start collecting all the packets for that stream. When you have them all, you can assemble them into the data stream and send it to the application. So the process is basically the same with TCPIP as with OSI, but again, in a variety of ways, it's more flexible. Okay, so again, quick comparison. TCPIP has only 4 layers, OSI has 7 layers. The correspondence application layer for TCPIP encompasses OSI's application, presentation, and session layers. And as we discussed, the sequence is more flexible, right? So I can share information across these layers pretty easily. These other 3 are about the same, and there's no physical layer in TCPIP. If you are interested, there's a little article here, basically OSI, the internet that wasn't. You can read up on why the OSI model didn't catch on and TCPIP did, but the story in the end is basically OSI was rigid and overspecified and nobody could agree on exactly how it was going to happen. TCPIP basically was more flexible and said, yeah, as long as the data is in the proper format, we don't need to worry at all about how these layers are constructed. I mean, sure, they thought about how the layers would be constructed, but the focus was on making sure that the interfaces worked. OSI model was more about making sure that the contents of each layer were structured correctly. Okay, so reality check. Of course, this layered abstraction is very nice. Does it hold in reality? Mostly, but not entirely. Okay, so for example, you have firewalls. Firewalls, they're technology on your machine, on your router. They're going to look at stuff that they normally should not have access to. For example, they might peek into the packets themselves as opposed to just looking at addressing checks. So the router, for example, might do what's called deep packet inspection, where it actually does some sort of diagnostic checks on the contents of the packets itself to try to recognize malware. So that's one case, right? Which of course violates the layered model. Other things, transparent proxies, when devices are passing through data to other devices connected. For example, if you have a router that's passing on data to other devices, but that router pretends it's like one of the endpoints. So that, since they simulate application endpoints, they get all the data, but instead of actually processing it locally, they pass it onward. So it's a little bit different there. And network address translation. So there are different ways where devices, I'll go ahead and mention this briefly. It's not really essential to this course though, but network address translation. Imagine if you have a router and connected to that router are several machines. If you know about IP addresses, we haven't really talked about them, but okay, so I have this router. It goes off to the rest of the world, to the internet. Here's a router. The router might only have one IP, well, it does, it has one IP address, but each of these devices could, in theory, have different IP addresses. But the router, right, so endpoints have potentially unique IP addresses, but the router doesn't necessarily want to share them with the outside world, right? For a variety of reasons. One thing is that you can have a pool of IP addresses that you can share among devices as you need them, so an organization doesn't have to pay for a whole big block of them. Another possibility is you just want to do it for security. You don't actually release your IP addresses, so bad guys on the outside have a much harder time of targeting your particular machine. So for a variety of reasons, the router might wish to conceal your IP addresses or otherwise transform them. Network address translation basically does all that. And again, we're putting an extra step in this layering process. So the router is going to have to look at the application that's being, so one standard way to use network address translation is to give each application port and IP address pair its own basically virtual IP at the router. And so again, you're skipping over some of these things. So the router knows what the application is. It's going to have that information. And it's going to use that to reconstruct the IP address for the endpoint. But in order to do that, it has to look deep inside the packet, right? So the router must look at some extra packet data to determine the application, right? So the packet header data, not just the address. All right, so there are various places in networking where, yeah, you skip around some of these layered structures, but most of the time for most things, yeah, the layered approach is used. And, you know, these ways that you bypass it are more interesting because they don't happen all that often. Okay. Now, many of you who are still paying attention, you're thinking, wow, that was a whole big bunch of stuff there. And it was a little confusing and scary. And what's going to be on the exam? And we're real worried about our grades because finals are rolling up and yeah, bad stuff. So what do you need to know? Well, the big things are this. What is an internet backbone? What are your tier 1, 2, 3 ISPs? What are peering and transit agreements? What are APIs? Why are they important to the internet? Right, we talked about that. What is routing? How are typical problems addressed? Right, well, if you recall, we went back through some of this, right? Where's my routing? There it was, I saw it. They're typically solved by bypassing and rebuilding the route. So if something fails, some component fails in the network, yeah, you're going to try to route around it. And the reason why you can route around it is typically because there are many redundant paths available, redundant paths and components. Okay. Very good. And layered protocols. We spent some time talking about that. So what are the layers? How are they defined? Why are they separated? Right? More generally, what are layers? We have the OSI 7-layer model. You should know the layers for that. You have TCPIP. Should know the layers for that and what they do. And the big picture, right? How are OSI and TCPIP different? Okay, so all of that is encapsulated in this helpful image, which will be part of the recording, and feel free to look at that. Okay, that's it. That's what I got for you. Questions on any of this stuff? Does this all make sense? Are we all prepared to become network engineers? We're going to switch over to the computer science department, learn about networking. Maybe, probably not. Anyway, well, networking is pretty interesting stuff if you find that sort of stuff interesting. But here we all are. All right.